Hi, so you want to know the basics of quantum mechanics? Great, you're in the right place. What is quantum mechanics? Quantum mechanics attempts to explain the behavior of subatomic particles at the nanoscopic level. It is one of the most successful branches of physics, and there are countless examples of scientific experiments confirming predictions made by the laws of quantum mechanics. What is a particle? One of the particles you will be most familiar with will be the electron. These orbit the nucleus of atoms, and the nucleus is made up of two other particles, protons and neutrons. The electron is an elementary particle, one of the fundamental constituents of the universe. Scientists have found that protons and neutrons are made up of other particles called quarks. Quarks are also elementary particles. Quarks are held together by gluons. Gluons are also particles, but they are different from the quarks. They are the particles that produce the strong force that holds the quarks together. Gluons are also behind the strong force which holds the protons and neutrons together within the nuclei of the atom. Gluons do this by mediating the strong force between the quarks or between the protons and the neutrons, as the case may be. The types of particles like electrons and quarks we can think of as creating matter, and the types of particles like gluons we can think of as creating the forces. There are four forces that we know of: the strong force, the electromagnetic force, the weak force, and gravity. The Standard Model of Elementary Particles. The Standard Model of Elementary Particles describes how all the elementary particles and forces in the universe behave apart from gravity. How gravity works in the quantum realm is actually not very well understood. We have the matter particles, or fermions, which are divided into quarks and leptons. There are 6 quarks, up, down, charm, strange, top and bottom. There are 6 leptons, electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. We then have the force carrier particles, otherwise known as gauge bosons. The gluons we have discussed already. The photons are particles of light and carry the electromagnetic force, which holds the electrons in atoms. The W and Z bosons carry the weak nuclear force, which is involved in some forms of radioactivity and plays a role in how the sun burns. Owing to the discovery of the Higgs boson in 2012, that particular particle has achieved something of a celebrity status. Countless Higgs bosons make up the Higgs field, and it is the interaction with this field that gives other particles their mass. For example, the top quark is interacting with the Higgs field, and this is what is giving the top quark its mass. And the final boson we turn our attention to is the graviton, which is a hypothetical particle that mediates the gravitational force. Quantum leap. In the early 19th century, it was theorized that at the subatomic level, energy can only be released and absorbed in discrete indivisible units called quanta. This means electrons have fixed orbits around the nucleus of the atom as their energy comes in discrete amounts. When the electron gets excited or de-excited, they will absorb or emit a specific quanta of energy, which will mean they leap from one orbit to another without inhabiting the space in between. This is called the quantum leap. In essence, there are places within the atom that the electron will be likely to be, and other places where they won't, as energy is being absorbed and released in discrete units. Particles behave like waves. There's a famous experiment in quantum physics called the double-slit experiment, which exposed something about particles that still surprises us today. Particles display both particle-like and wave-like behavior. In a version of the experiment, on a larger scale, we have a gun that shoots tennis balls one by one at a detector, which will register where the tennis balls land. In between the gun and detector, we place a barrier with 2 slits, which will leave openings for any tennis balls to go through. Over a period of time, and after many tennis balls, a pattern emerges on the detector, indicating where the tennis balls have landed. The results show that the balls which have not been blocked have landed directly behind the slits in the barrier. If we replicate this experiment, but on the subatomic scale, and use electrons instead of tennis balls, we expect similar results. But this was not the case. Scientists found that when the gun shoots electrons one by one toward the detector and past the double-slit barrier, the pattern that emerged on the detector looked like this. The electrons landed not just behind the 2 slits, but in narrow strips across the length of the detector. and a significant number of electrons even landed straight behind the middle of the barrier. The pattern that emerged is an interference pattern and is associated with the behavior of waves. Imagine we have two waves that interact. The peak of the waves will combine to form a higher peak, and the troughs will combine to create a deeper trough, and when a peak and trough meet, they will cancel each other out. So if we imagine that our electrons are less tennis ball-like and more wave-like, then what happens? This is a wave from above. The black lines represent a peak, and the spaces in between are the troughs. When an electron goes through the double slit, its wave is split in two, and these waves then interact. The peaks meet here and reinforce each other, creating higher peaks, and the troughs meet here, also reinforcing each other, creating deeper troughs. And here a peak and a trough meet, cancelling each other out. The interaction between the waves results in the interference pattern at the detector screen. Where the waves are most intense, we find more of the electrons on the detector screen, and where they cancel each other out, there are no electrons on the detector screen. Erwin Schrödinger came up with an equation for the electron's wave function, and using this equation, we can find out the probability of the electron being in a particular location. Think of the wave as a bundle of probabilities, and the size of the wave in any location predicts the likelihood that the electron will be found there if it is looked for. That is why on the detector screen we observe most of the electrons landing in the places where the electron's wave is at its most intense. It seems as if the electron is not in a fixed position but has different probabilities of being in many different places at once. The act of measurement. To observe the electron's wave function going through both slits at the same time, detectors were placed next to the slits to capture this activity. But when this was done, something strange happened. The electron stopped behaving like waves and went through one or other of the slits and landed on the detector screen to form the two-striped pattern rather than the interference pattern. It seemed as if the act of measuring did something to collapse the wave function. The superposition principle. The superposition principle states that while we do not measure the electron for its position, it is in all the possible positions it could be in at the same time, and when we observe it, the superposition collapses. So in this illustration, when our detector is off, our electron is in all of the possible positions or states it could be in simultaneously. But when we switch our detector on, the superposition collapses and the electron gives up all of its possible states to choose just the one. That is why we were not able to observe the electron's wave function going through the double slits. The very act of attempting to observe made the electron's wave function collapse. The electron gave up its superposition and chose just the one state to be in. i.e., the electrons actually reverted to particle-like behavior, and that is why instead of going through both of the slits, the electrons that landed on the back detector chose to go through either one or the other of the slits. Let's use one of the most famous thought experiments to further illustrate what quantum mechanics is saying about the electron and the superposition. We turn our attention to Schrödinger's cat. Schrödinger's cat. Erwin Schrödinger described a thought experiment where a cat was placed in a covered box with a radioactive sample that has a 50% chance of decaying and killing the cat. While the box is covered, we have no idea if the cat is dead or alive, and only once we open the box will we know if the cat made it or not. So if the cat were similar to an electron using the superposition principle, we would say that while the box was covered and the cat was not being observed, the cat was both alive and dead at the same time, in order for it to be in all the states it could possibly be in. Only when we lifted the cover to observe the cat did its superposition collapse for it to be either alive or dead. Obviously this feels intuitively wrong, and the reason why this thought experiment was employed was to illustrate how odd the laws of quantum mechanics are when it comes to describing the behavior of particles. However, countless experiments have corroborated the results predicted by quantum mechanics. It does indeed seem as if particles have a wave function and that particles are in all the states it could possibly be in simultaneously until it is observed. But why do we see evidence of wave-like behavior from particles and not cats? After all, cats are made up of particles. Well, the reason is, the bigger the object, the smaller its wavelength, and at the size of a cat, the wave is simply too small to be detected. Time-traveling electrons. Another way scientists have tried to observe the electron's superposition in the double-slit experiment was to observe them after they had passed through the slits. So they placed detectors in between the barrier and the detector at the back. The reasoning was that as the electrons passed through the barrier, their waves would have split as there was no measuring happening while they went through. And then when they were measured past the double slit, the electrons would be found across the length of the area behind the double slit barrier and in correspondence with the final interference pattern. But that didn't happen. In fact, when they did the experiment, the electrons were found only in the areas directly behind the slits, and no interference pattern emerged on the back detector. Stranger still, when the detectors were switched off, the interference pattern returned. When scientists weren't looking for the electrons, they continued to exhibit their wave-like properties and land on the back detector to produce the interference pattern. But when the electrons were observed, they collapsed back to a particle and eliminated all evidence of the superposition by not being detected anywhere but behind the slits. So the scientists attempted to outsmart the electrons and decided not to have the detector switched on until after some of the electrons had passed through the slits. But even when they did that, the electrons somehow knew that the scientists were going to switch the detectors on, and the superposition collapsed. There was no interference pattern and electrons were only found behind the slits. Every time the scientists decided to leave the detectors off for the whole of the experiment, the interference pattern emerged. And every time the scientists decided to turn the detectors on midway through the experiment, the interference pattern no longer appeared. So it was almost as if the electrons were going through the slits with their wave function intact, and as soon as they realized that the detectors were going to be switched on, they went back in time, reverted back to particle-like behavior, and erased all evidence of the superposition. So what's actually going on here? Are the electrons actually time traveling? Well, quantum mechanics says that the electrons did not go back in time, but that they did in fact go through both of the slits at the same time, but that as soon as the detectors were switched on, the electrons collapsed their wave functions, choosing to be in line with one or other of the slits and erasing all evidence of their superposition. The many worlds theory. So now we know that measuring appears to have an effect on the behavior of particles, and there have been many theories to explain this. A few notable ones are the spontaneous collapse theory, Bohemian mechanics or pilot waves theory, and the many worlds theory. Of all the theories, the one that seems to have captured popular imagination is unsurprisingly the many worlds theory, so we will touch upon that briefly. The many worlds theory states that anything that can happen does happen. Before we attempt to measure the electron, quantum mechanics says it is in many states at once, and the act of measuring collapses it to only the one state. The many worlds theory states that in fact when the measurement happens, the electrons will collapse to all of the states, but different worlds will observe different results. So in fact, instead of one world, there are many different worlds, and in world A, you may see the electron turn up in position A, but in world B, your clone will see an electron turn up in position B, and so on and so forth. The implications of this are mind-boggling. Every time there is one or more possible option available for the universe splits and creates copies where all possible outcomes come true. So for example, there could be a world where Hitler won World War II, a world where mankind never made it to the moon, and a world where penicillin was never discovered. But there could theoretically be worlds that are much more advanced than us. A world where we have glimpsed further and deeper into the workings of the universe and have been able to achieve immortality. If that was the case, then every person has achieved quantum immortality in one alternate reality or another. Introducing quantum entanglement. Quantum entanglement occurs when two particles become connected in such a way that when the property of one particle is changed, an instantaneous change in the property of the other particle occurs. Entangled particles have the opposite properties or states. Particles have a property called spin, and the particle will either be spin up or spin down in any given direction. When two particles are entangled and their spins measured in the same direction, one particle will be spin up and the other particle will be spin down. According to quantum mechanics, a pair of entangled particles could be separated by an entire universe, and when the state of one is measured and its superposition collapsed, it would immediately collapse the superposition of the other particle, and measurement would indicate that it had the opposite state of its entangled partner. So in this example, particle A and B are entangled and separated by an entire universe. They are not measured and have the superposition of being both spin up and spin down at the same time. When particle A is measured, its superposition is collapsed and it indicates spin up, and as particle B is entangled with particle A, its superposition is also collapsed and it indicates spin down. Quantum mechanics seems to say that entangled particles can communicate with a speed faster than the speed of light, something that Einstein's theory of special relativity ruled out. Einstein called this phenomena spooky action at a distance. Einstein was not impressed by the explanation given by quantum mechanics to describe the behavior of entangled particles, and he actually offered up his own alternative theory. He said that when the particles were entangled, it was decided what states they would each have when measured in any given direction, and there was no communication happening between the two particles when they were measured after they had been separated. According to Einstein, the particles didn't have some mysterious superposition of being both spin up and spin down until measured, but rather at the point of entanglement it was decided what spin one would have and what spin the other would have in any direction it was measured. Einstein's explanation versus quantum mechanics explanation. Professor John Bell actually came up with an experimental way to test whether quantum mechanics or Einstein's more classical explanation worked when it came to explaining the results entangled particles gave when measured for their spins. What emerged was that Einstein's explanation broke down, and the predictions made by quantum mechanics were consistent with the experimental results. The experiment proved that the spin of the particles were not defined specifically in all directions of measurement when the particles were entangled, as Einstein had theorized. Introducing quantum tunneling. In a phenomena called quantum tunneling, it has been observed that particles have the ability to cross barriers they shouldn't be able to. The reason for this is down to the particle's wave function. Let's use an example. This particle here shouldn't have the energy to be able to cross this barrier, but it can, and that's down to its wave function. Even though the probability of finding the particle on this side of the barrier is low, it is not zero, and the particle can indeed tunnel its way to the other side of the barrier. Quantum tunneling is responsible for nuclear fusions in our Sun. In the Sun, hydrogen atoms fuse together to create helium and other heavier elements, releasing huge amounts of energy in the process. The hydrogen nuclei consist of positively charged protons, and as like charges repel each other, fusion only occurs when a huge amount of heat is applied to overcome this barrier and force the protons together. However, the Sun isn't hot enough to give the protons the energy required to overcome their repulsion. The reason why the protons can overcome the repulsion between their positive charges is down to quantum tunneling. Owing to the proton's wave function, there is a small probability that some of them will tunnel across the barrier and fuse with the other proton, creating heavier elements and thus fueling the Sun. Why do we accept quantum mechanics? The predictions of quantum mechanics have proved so reliable that we cannot ignore the experimental evidence that corroborate the theory. The entire electronics industry is built on using quantum theory. Those principles have led to the invention of lasers, transistors, and the integrated circuit. The future of quantum mechanics, the quantum computer. The first quantum computers are currently being developed. Harnessing a particle's ability to be in many states at once means that multiple processes can be executed simultaneously, increasing our computing power exponentially. Our lives have already been changed dramatically by technology, and when the power of quantum computers is realized, it will herald the dawn of a new era in technological advancement. The future of quantum mechanics, teleportation. Using quantum entanglement, scientists have been able to teleport particles. Two particles are entangled and separated by a large distance. A third particle, particle T, is brought in, and this is a particle that we want to teleport. This particle T interacts with particle A, and we learn how the quantum state of particle T relates to particle A. This information is then sent across to where particle B is kept. As particle A and B are entangled, this information about how the quantum state of particle T relates to particle A will also reveal how the quantum state of particle T relates to particle B. Particle B will then be manipulated to replicate the quantum state of particle T, becoming an exact copy of particle T. Meanwhile, the original particle T is destroyed as its information was extracted and sent across. This method of teleportation has only ever been done on particles, and a single human being contains a huge amount of particles, and that would mean an immense amount of data would need to be transferred for human teleportation. Transferring this amount of data using the means we have today would take upwards of 250 years. At the same time, it opens up a philosophical debate of whether the teleported particle T is actually the original particle T or just a precise copy of the original particle T. Imagine that human quantum teleportation became a reality. Say Alice wants to travel from London to Tokyo. 2 chambers of entangled particles would be in each city. Alice would step into a scanning device and the quantum state of each individual particle would be measured in relation to the chamber of particles in London. This information would be relayed to Tokyo, where the chamber of particles would be manipulated to replicate the quantum state of each of Alice's individual particles, creating an exact replica. Meanwhile, the original Alice in London has been destroyed. The question is, as the original Alice dies in the process of teleportation but is then reconstructed at her destination in Tokyo, is that still Alice? Tokyo Alice is identical to the last atom to the London Alice and is in full possession of London Alice's knowledge, experience and memories. And Tokyo Alice even believes she is the London Alice, while the original London Alice no longer exists to debate the issue with her. It's a philosophical and ethical dilemma, but it may not be one that we will need to face. Human teleportation would be extremely difficult, so although it is not impossible, it is improbable that it will ever become a reality. Quantum mechanics and general relativity incompatibility. Quantum mechanics and Einstein's general theory of relativity are 2 of the most successful theories in physics, but they are incompatible. Quantum mechanics describes space and time as being quantized, whereas general relativity describes space and time as a smooth continuum. String theory attempts to resolve the incompatibility and is an attempt to find the elusive theory of everything that explains all the matter and forces in our universe. That in itself is a whole other video. This video has attempted to explain quantum mechanics for the layperson who wants to know what it's all about. It is a simplified explanation and can be used as a springboard for further study. As always, we hope you found this video enjoyable and informative. Make sure to subscribe to London City Girl for more interesting videos. Thanks for stopping by and supporting our channel, and we'll see you next time.